There are a whole range of streetcar modifications that I see. Most are supposed to be about performance, somehow convincing whoever the car is now faster. I'm not a fan of these, and I think most are just a bit dumb. Then, not very long ago, there came a piece of plastic that I really thought was an elite level of stupid. It is an Australian thing, as it is a piece that is designed to sit above the rear window of a sedan or notchback in the style of a Holden Commodore or Ford Falcon, though I have seen them on other models. I hope these don't appear in other countries. So I ran this in a simulation and then compared it to another aftermarket design meant for an MX-5 Miata. I have wanted to do this study for a while, so finally. After that, I dig into the particular efficiencies that characterize the aerodynamics of the C-pillar. A properly shaped C-pillar can reduce drag significantly on a well-designed vehicle. There are parts that suggest performance, and here, without the advertising saying so, it is supposed to add downforce. My guess was that it was going to increase drag by increasing the size of the wake. But will it decrease lift, and therefore, in theory, increase performance? Nowhere does it say that it will increase performance, only that it will apparently make you stand out. So here we are, going to find out how much stupid that costs $150 can make you stand out. Before placing it on the notchback model, I revised the baseline, which now aligns better with the experimental results of a CD 0.246, such that it is now 0.2476, just 0.65% off, which is better than the 5.69% previously. Adding the spoiler, it increases the CD to 0.269, 8.6% more drag. Therefore, because it is draggier, you would hope that it would have some downforce to make it worthwhile. Lift didn't change from the zero it has as the baseline. Awesome. At least with the estate model of this car, the extra drag came with downforce. Therefore, those who put this on their car, such that paying a couple $100 for a piece of plastic, you are still paying for it every day, dragging it around, burning fuel. But you know, at least you stand out. Anyway, that's pretty negative and I don't like that. So we're going to move on to another piece I found. A custom roof for an MX-5 Miata, with these apparently functional extrusions. The culture around these cars is completely different, and I was far more optimistic about this than the previous piece of stupid. It's a whole roof, so much more expensive, and it's buying into a subculture orientated towards extracting performance from a low-powered vehicle, which means efficiency is a high-order goal. Imagining air flowing over this roof also made a certain amount of sense. A first guess is that it creates two interacting or complementary flow structures. There is an A-pillar vortex in there as well. The vortex from each will likely stick near the body, helping the air fill the wake in a controlled manner. Some images from the internet show the addition of a roof on an MX-5. A canopy is better than nothing, then a hardtop is an improvement on top of that. Such a steep rear roof section isn't conducive to flow attachment, and it appears air is circulating with a lower streamline becoming more turbulent. This steep rear window isn't the same on the driver model, but it is still a bit messy at the rear interface between the glass and the boot lid, so there is a chance I could replicate a positive result, if there was one that is. We are here, so yes. A bit more analysis of the rear of this baseline starts with the recessed rear window. The theory says it helps preserve the boundary layer and delay separation. Therefore, there is still concern there is separation from the designer of this model. there is a channel running along the edge of the roof. Above the doors, it goes all the way back to the boot lid. This turns out to be a rather nice piece of aerodynamics for resolving the interaction between the three surfaces, side, top, and back. Noticing this on cars in the wild, there has been a focus around this specific part of the car. However, there are better solutions we will get to. Adding the pieces to replicate that seen on the MX-5, there was a noticeable difference in a positive way, which is nice. Drag is reduced by 3.4% to a CD of 0.2393. There was a little less lift as a bonus. This is even better than the fastback version of this model, as it has a CD of 0.243. It has a higher rear. Looking at the LM2 ISO volume alone, I would be skeptical. But then the pressure map with the streamlines on the surface looks far more coherent with the added geometry. The wall shear stress map, attached flow structures pulling at the body. The center of the body is far less symmetric on the baseline. This suggests that the wake is more controlled by adding the surfaces. Another way to look at this is through the percentage of drag from shear stress and pressure. Body drag from pressure is now lower at 0.213, or 89% of the total, compared to the 0.223, 90% of the baseline total. To get a significant drop in the CD, it is always going to be pressure driven. So I think from this result, I can be confident in saying that the aftermarket roof the Japanese producer is selling would have a positive aerodynamic effect over a roof that doesn't have these protrusions. Bear in mind that the MX-5 is a convertible, which will not have a very good drag number, as high as a CD between 0.37 and 0.44. A bit more analysis, this slice through the space, is probably the best way to look at this important volume over the C-pillar. On this particular model, the vortex created by the top protrusion doesn't seem as important as the ones on the side. I added two to try and save time, rather than find the best placement of one. It's the upper one that seems to be doing the most, reducing vorticity on the upper section of the C-pillar. The Lambda 2 isn't the most appropriate scale, but it has the correct basis. It is the tealed coloured puddles that represent the drag components that would want to be reduced. A vortex in red, it is a product of the pressure gradient. But an oversimplified statement, the red represents a smaller vortex than the blue and will have less energy. I probably should have stopped here, but that was 3 weeks ago. It was just that there has been 10 years of development on these cars since this model was released. With this amount of gain, from what amounts to a fairly crude addition to the C-pillar, and starting from scratch, this section can be altered to an infinite degree, embedding drag reduction into the surface. Now, I almost got through a full alphabet of cases, and it doesn't seem like a good idea to present them all. A bunch weren't improvements, so I thought I would present 3 categories and talk about the transitions. First is the breaking down of the initial model. There are 2 baselines that can be formed, in which I was able to glean a broader understanding of the aerodynamic concept of the notchback sedan. After the previously mentioned case, I wasn't able to find a better solution with additional pieces added to the pillar, which meant that the next step was to pull the window out flush with the body and give it a bit more angle, aligning it to the C-pillar base. The task required to blend the roof ridge into a smooth corner. Replacing the surface at the corner was complex, and initially it was a lumpy solution. Running this gave a CD of 0.375. a 4% reduction from the baseline. Over this C-pillar, there seems to be two main volumes. First is the transition from the side and roof to window, where the vortex from the A-pillar wraps itself over the roof upstream of this transition. This transition is where the extrusion was placed on the initial model, cutting through the low pressure volume, as a consequence shrinking it. Below this volume is the transition from the side and window to the boot lid. It seems that the lump in this transition for the recent model disrupts the smooth flow passing over the boot's corner and into the wake. On the baseline, a vortex is shed from this, creating a delineation between the side flow and top flow. Cleaning this pillar up will form the next two baselines. The thinking was that building a smoother transition, particularly around the lower part of the pillar, should eliminate the vortex and the energy that drives it. The first is just making the C-pillar as coherent as possible. The result is a CD of 0.468, slightly less than the base model. One of the first things to do on this model was to add the side protrusions, which gives the exact same CD of 0.2393 as the MX-5 replica editions. Later I also added the roof protrusion to give it CD 0.2417, and this was all pressure driven. Digging into these three cases, particularly why the last one doesn't perform so well, comparing the two baselines, the C-pillar characteristic is consistent as shown by the similarities with the shear stress maps. The windows are clearly different as a result of the flush window and more angle. With the protrusions, the recessed window needs a rooftop protrusion more than the smoother model. Cutting up the C-pillar's low pressure areas are clearly important. The only other case worth mentioning is where I added a longitudinal piece across the apex of the window and boot at the side, almost getting the same result as the side protrusions, with a CD of 0.2402. On the smooth baseline, a vortex is established, but delayed off the back. Seeding it at its place of origin is apparently worth a 2.7% reduction in drag. Now lastly, before I wrap this up, adding a crease through the lower C-pillar volume embeds any addition into the surface. It was an attempt to deliberately achieve something that the lowest drag model did. It is also similar to the current Camry model. A bit far off the result though, but better than the previous baselines, with a CD of 0.2448 and 1.2% on the original. Cutting the upper low pressure area gave a CD of 0.242. These numbers are really close to each other, so how much confidence do I have in them? Counting to the third significant figure, I'd be reasonably confident that the delta is accurately pointing in the right direction. But then, this model doesn't exist in the wild, and the subtleties are such that the best drag result I got comes from a modelling inaccuracy. All this means is that there is decent gains in efficiency by addressing the flow over the C-pillar. This is reflected in the developments manufacturers have placed on designing this part of the car. I wouldn't recommend sticking something to the C-pillar of your car and expecting it to work. It wouldn't be as bad as sticking that spoiler on, which we saw in the first model. But saving 2% drag on a car driving around in the wild would be super difficult to measure. Not impossible, but difficult.